Yeah, good morning. My name is Roger Fritz. I've known several of you guys for quite a while, quite a few years. Um, I'm head of the Nikola Tesla Collaboration Group, and I wanted to present to you today the group from Canada in Montreal that have developed the SmartD drive control and to basically discuss the advantages of why it's so important to have pure sine wave, VFDs for multiples of applications. Um, I've been in the motor and drive industry my entire life, over 40 years doing work with multiple power companies on drive controls. My father started back in 1953. You can see my fourth generation grandson, or his grandson, that's my grandson. Um, and he had been in, business since 1953. He'd been putting up wind chargers way back in time when they're starting putting power in the, western part of Nebraska. Um, if you do want to join this group, you're more than welcome to. I do own this, what I call the Tesla Bible, that talks about all the different devices that he had done in rotating machinery. And you're welcome to join that group if you'd like to. This is just a short video, a little bit about Tesla.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability of alternating currents.
A clean power VFD uses a pure sine wave outright, eliminating the PWM drawbacks. It also brings additional benefits such as more energy savings, a reduced footprint, and simplified installation and maintenance. Common mode voltage is created by VFDs switching IGBTs on-off continuously. This causes wear and tear on the motor bearings. The first sign of bearing damage is audible noise due to the bearing balls traveling over the pitted and frosted areas. How are these pitted and frosted areas created? Fast switching of the IGBT creates parasitic capacitances in the motor. Common mode voltage and capacitances are sources of a shaft voltage. Shaft voltage causes arcing through the bearing lubricant, which results in pitting on the bearings and fluting on the bearing races. dV/dt of the common mode voltage in the stator windings generates pulse currents flowing to the rotor. Part of this current flows between the inner race and the outer race of the bearings, causing heat in the lubricant. Common mode voltage generates an electric charge stored in the parasitic capacitance between the rotor and the stator. When this charge gets high enough, it breaks the dielectric insulation and is discharged through the insulation of the bearing. The capacitive discharge current can cause fretting of the bearing and raceways and produces temperatures high enough to melt the bearing steel and cause pitting. If the motor frame is poorly grounded and the motor is connected to a mechanical load that has a proper grounding, low impedance, the common mode current flows through the shaft reaching for the lower impedance. Clean power takes advantage of the latest generation of power transistors, advanced algorithms, and optimized integrated filters to produce the next generation of VFDs without common mode voltage. A clean power VFD is the solution. A three-phase clean power VFD produces three smooth sinusoidal waves, which at any point average a sum of zero. This creates an optimal scenario with zero common mode over voltage. The best solution to mitigate common mode voltage is to not generate it. A clean power VFD produces a clean signal with no need to mitigate common mode voltage.
Just listen to the difference. When a standard PWM inverter drives the motor, you hear the harsh switching noise, audible evidence of compromise. Now switch to the SmartD pure wave inverter. The same motor, but the sound is smooth, clean, and nearly silent. That's not just quieter, it's smarter. Superior waveform, superior operation.
So the reason I bring that up is over time, I've been involved with thousands of VFD installs, and what always comes up is a lot of times when you get a multiple VFDs. Some of the first ones we ever did for Milton Bradley Toys, we ran into tremendous harmonic content on the front. So the way to patch that, we were putting line reactors, active front ends to clean that up, because it creates radiated noise out through the system on the primary side with the diode front ends. With an active front end drive, that cleans itself up, and then on the back side, the output waveforms, we had to make sure that the motors were very well tuned, make sure we didn't have grounding currents, rolling through the shafts to cause bearing damage. With a clean pure wave output sine wave, the actual leads going out, you don't need a special VFD cable, which is basically armored cable that goes over to get rid of the noise. Plus, you can go along lead lengths without getting coupling that actually amplifies the voltage, like on submersible pumps and those types of things. So I want to introduce you to Josh today. He's an associate I've known for a while, with SmartD, and he's been with them quite a while. And, he can share it from here.
Great stuff. All right. Well, thanks everyone for joining in, and it's going to be a lot of fun going through this. I'm just going to share my screen here. And what I've done is I've taken, we talked about Chris Richards earlier. He's just joined us, so hello to Chris. But we've taken, here we go, taken Chris's PowerPoint and I've tweaked it. So Chris, of course, works for SmartD as well. And he takes care of the Western U.S. areas, that is the national sales manager, and covers that area there.
Hey,
so go ahead.
Quick note, Josh, if you don't mind, guys, that there's a few people on that call, but feel free to go ahead and use the chat to ask your questions. We'll address them at the end for the bigger or more specific questions. But if you have questions about what Josh is talking at that moment, Roger or I can cut him off during the presentation. We can address a question right away. So feel free to go ahead and ask your questions on the chat. And as we're, again, not too many, if you're comfortable, you can also unmute yourself and ask that question yourself. Don't worry about it. Sorry about that. Go ahead, Josh.
No, rock and roll, man. That's good. All right. So the very first slide here, what I just want to look at this image over here, and we want to come back to this later. This here is a completely fully filtered drive. It looks like a VFD. We put it into a NEMA 4, NEMA 3R panel. But this has all the line and load filtering you'll ever need, all the advanced filtering, but you don't see any of the additional stuff. So we'll go through that in a second. Of course, you all know the advantages of the VFD, whether you're optimizing energy or you're trying to get your processes in place and get some accuracy there, or whether you're maximizing the longevity of your system due to mechanical stresses of starting. So it is the softest start in the industry available, and with full torque control, something a soft starter can't give you. Now, with the adjustable speed drives, as many of you may know, there's line side impacts. So on the line side of the VFD, you get your harmonic distortion, and that causes problems upstream from the drive to the grid and so on. It also contributes to what we call common mode voltage on the back end. And of course, there are specifications, IEEE 519, that require that the total harmonic distortion be less than 5% or 8%, et cetera, depending on what your characteristics are for that application. And then how do you mitigate that on the line side? Well, there's good, better, best. There's reactors. You can go with multi-pulse drives. You can go with passive harmonic filters, active harmonic filters. So let's continue on with the line side impacts. So a traditional standard VFD will have a diode bridge, of course, that rectifies and brings this wonderful AC wave and turn it into a DC. And then it'll turn around and finally chop up that DC signal with these switches called IGBTs. And that results in a square wave going out to the motor. It doesn't look like a sine wave, but it's trying to simulate a sine wave, as we all know. So there's loss of energy at rectification, and then there's also loss of energy in having a simulated sine wave. How we get around that? Well, some people will just, they're not looking to rectify anything on the line side, so they just leave it as a 6-pulse rectifier, a standard VFD, a naked VFD, if you will, and your harmonic distortion is going to be 35 to 85%. Then you can also make it a 12-pulse rectifier where you multiply the number of diodes and you end up with 12 instead of 6, and your total distortion is a little bit better. You're about 12%. And as you continue to increase your diodes on your front end, you can get that distortion down to 8 and then finally to 3 with a 24-pulse rectifier, which is kind of rare. We see that a lot in a medium voltage. They'll go up to 32 and higher on the medium voltage. But on low voltage drives, ideally, if you can get a 24 pulse, you've got a really good sine wave kind of being drawn from the grid. And of course, people are still using these IGBTs when they're doing it. And we're going to address that in a moment here. The problem with it, all of this, is you're still not addressing the back end. And we'll continue on from there. So on the line side, the traditional ways of mitigating these things is we'll put in, again, a good, better, best solution. We'll either go with a line reactor, passive harmonic filter, or an active harmonic filter. And then we have to put them all into a cabinet. And you see these cabinets here, they're pretty gigantic. This is just the VFD here. But now we have to make a cabinet large enough to house everything. And so you end up with these 6 and 8 foot cabinets and so on. So that increases your costs for your sizing, increases labors, of course, transporting them from manufacturing to site, etc., maintenance, power consumption, and energy losses. So it gets rather cumbersome. The active front end came along, and that's where they took, if I just go back here, they took this rectifier bridge and they took everything on the back and put it on the front. And now you've got a back-to-back drive. So this is what an active front end is. So the front end is active. It's constantly monitoring the harmonics and what's coming in, just like an active filter, but now it's inside of the drive. But it's still IGBT based. So there's still some challenges with that because IGBTs have been around for about 40 years. And even though we keep increasing their ability to handle heat and things like that, you're still going to have to deal with a square wave signal. And you now have to introduce some very large mitigation on the front end as well. So we have a rectifier, we have a DC bus still, which is awesome because then we don't have any voltage drop issues. We'll get to that in a bit. And of course, on the inverter side, it's still a IGBT based inverter side, but you can get your harmonic distortion down to less than 5%, and you get to reduce your footprint. So let me just go back here. If you got an active front end here, you can knock out the active harmonic filter, one of these guys. All of these guys are gone if you've got an active front end. So that helps reduce your footprint. All right, now we mentioned very briefly that other people have taken this active front end idea and they've tried to play with it. One of them, if for example, is called a matrix drive. And in a matrix drive, there's no DC bus. And so it's a great experiment. It is basically a multi-pulse drive in a sense, but you're going to have a loss of voltage drop between the input versus the output. So you have a sizing issue. It's very sensitive to shock loading and things like that, and grid disturbances. So even though it's a nice little experiment that they tried, it's unfortunately it's got a lot of drawbacks to it, and you're still dealing with a square wave to your motor, and that's probably one of the main theme that we're going to go with here for a bit. However, the matrix is also able to get to that 5% harmonic distortion, which is preferable. So just a quick review on that first part here on the line side problem, line side harmonics. A standard VFD still has this output signal that's a square wave. Even an active front end, all the active front ends out there, typically up until this point in history, still have a pulse width modulated square wave. And then, of course, any of the experimenting of the active front ends that's been happening, they still have this drawback, not only in the design, but still with a square wave to the motor. So we still have an impact going there. Now let's talk about the load side. So we just finished talking about the input side. Let's talk about the output side of the VFD. We have a square wave trying to pretend to be a sine wave, and that causes a lot of issues to the cable and the motors. So you have voltage spikes, corona discharge in the cable, which can break down the cable insulation. These voltage spikes can break down the motor insulation. That shortens the motor life. You also have leftover energy that's common to all three phases and to ground, and that's the common mode voltage. And that starts to show up in discharges in the bearings of the motor, what we call shaft currents or bearing currents. And then you have to put insulation on your bearings and so on. So what you end up doing is you end up paying more for the insulation of your motor, the insulation on your VFD cable, anything on the bearing has to be insulated, and then the shaft ground has to be introduced. You have to watch out what kind of lubricants you're using, because they could be conductive over time. They can break down, and so on and so forth. So this really shortens the motor life and can shorten the cable life, and there could be some catastrophic failures as well. How do you mitigate that? Well, you got to pay extra for inverted duty motors, which can handle the spikes. Special VFD duty cable. You can still use shielded cable, but really what you're after is the insulation of the cable to be able to withstand these voltage spikes as well, and the corona discharge. You can introduce common mode chokes or insulated bearing shaft grounds, like we mentioned before, and then external sine wave filters. And again, with the external sine wave filters, we'll talk about that in just a second. Here we have what a schematic is of our VFD. You've all probably seen this already.
Sorry, Josh. I'll cut you there for a second. We've got a question by Emre. Does square wave act against soft start?
Sorry, what's the question again?
Does square wave act against soft start?
Square against soft start. If I understand the question correctly, are you talking about a soft starter versus soft starting? So
we did have an answer here from Kevin Baker. Not as such. The VFD is a soft starter by the fact that it controls both voltage and current to the motor. The output waveform doesn't bear on the soft start function.
Right. So if the question has to do with the soft starting function of the VFD, then yeah, Kevin's correct. It has no bearing on the ability to just magnetize your motor and bring it to speed without any inrush current. So that's not an issue at all. If you're talking about versus a soft starter, so soft starters have their own topology and whatnot with SCRs, and the like. So that's a completely different topology. But
Yeah,
there you go. Perfect. So here's a schematic of the VFD. And we have power coming in on the rectifier side. Here's your DC bus. And of course out to the motor. And these switches here, the IGBTs, they have an algorithm that allows them to switch in tandem, in pairs, and simulate this square wave going out to the motor, right? So that could be basic for some, it might be new for others. And what happens is this signal, depending on how long your cable is, it'll start to distort on this back end towards your motor. So so this square wave, which is already a simulated sine wave, now turns into something that's a little more freakish. And the longer your cables are, the more it distorts. And that's because there is not all the energy is being used by the motor, because it's not a pure sine wave. So that energy has to go somewhere. So it ends up reflecting back and starts adding to the spikes and the switches and so on that occur when you chop up this DC signal. So at the edge of one of these little lines here, there's a little spike. I don't know if you could see it. It's probably not the best picture, but it ends up amplifying the spikes so that it looks like this. And that starts to hammer and pepper the insulation on your motors. And that's what breaks down your motors and breaks down your cables over time. There's another component to it, and that's more leftover energy called common mode over voltage. And so this continues to attack the bearings in your motor by trying to find its way to ground. And you can see an example here of what happens with pitting or frosting or fluting. What happens, frosting is actually the first thing that happens, because the discharge that happens every time this energy tries to find its way to ground, it starts to change the metal in the bearing, and we call it frosting. So it makes it very soft, and that can lead to pitting, it can lead to fluting, etc. And then you end up having ground faults, and it is very expensive, and then you have unexpected downtime, etc. So if you got critical applications, this is where we want to make sure we're mitigating all of that. So a common mode choke gets put in for a lot of people. Some people will buy a reactor, or they'll spend more money for a DVD-T filter, or they'll spend the most money for a sine wave filter. And that can also go in line on the load side of the VFD. You'll have to buy an inverter duty motor, what we call a NEMA MG1 Part 31 motor. And all of this is because we're trying to make this square wave look like a sine wave to the motor. And this is just a summary of all the mitigation we do against all the common problems on the back end of your VFD. Of course,
Josh,
yep, go ahead.
could you give a quick note about Jody? The video we just received this morning from the agricultural client had a common mode voltage. It was similar. It was caused by that, right?
Yeah, there was a lot of line noise. So common mode voltage causes that line noise, but also on the front end. So we're looking at the back end right now, but on the front end, if you remember, there's also the harmonic distortion that happens, and that starts to add a lot of emissions and noise into the grid, and affects everything else connected to the grid. So if you've got sensitive equipment, like that farm was, that was a highly automated farm, and all of their equipment's being affected by these emissions happening from the VFD on both sides, right? So, but the line side contributes to this common mode as well. It's not just this back end. So yeah, so that was a perfect example. There's a video that Thierry was able to put together with this gentleman's testimonial on his farm, and how he's able to solve that with the SmartD solution. So coming back to this presentation, was that okay, Thierry?
Yeah, perfect. Thank you.
Okay, great. So coming back to this situation where we're adding all these types of filters and trying to mitigate this problem, again, we got to package it all into these large cabinets. And that, again, costs a lot of time, labor, transport, maintenance, etc. And of course, facility footprint. So now let's talk about the SmartD solution to the line and load side. We call this the clean power VFD. And the reason why it's clean power is because we're able to draw a pure sine wave from the grid, and we're able to output a pure sine wave to the motor. What we've done is we've taken the active front end idea, and we've put, instead of IGBTs, we're using this thing called a silicon carbide MOSFET. Now, these MOSFETs are a type of switch that switches 20 times faster than the 40-year-old IGBT technology that everyone's been using in the VFD industry forever. We never had access to these type of switches because it was so rarely used. They were very expensive, they're very inaccessible, and they weren't necessarily as mature in the way they've been built, etc., until now. The EV market has really made these things accessible, really matured it, and now we're able to bring those into the VFD world, and it's changed the game. And we've made sure we put 6 patents on this thing because it's completely changed the way we're now going to run facilities in the VFD world. So it's a silicon carbide MOSFET. That's the big game changer. We still keep our DC bus, so there's no loss of voltage drops and things like that. It's not sensitive to the grid shocking. And we have the MOSFETs on both ends, the back end and the front end. Really, we started with the back end to get that clean sine wave. Then we turned around and put it on the front end. And we have clean power, and we have a sine wave. Now, let's talk about the secret recipe in this. So the silicon, again, in the 50s, we started with IGBTs. And then now we're able, right around 2018 or so, and just before that, because of the EV market, we're able to access these MOSFETs and bring them in. And these are part of what we call the wide band gap semiconductors. And wide band gap semiconductors, you have silicon carbide and you have gallium nitride. And this graph just shows all the different industries that those switches are used in, and which are now being put into the market at an exponential rate because of what they can do for power. Now, you don't get something for nothing. Even though you're getting better switching, better power density, less losses, you can handle heat so much better, and the sizes are so much better. We do have a higher EMI or a higher DVDT spike if we just use these switches without any mitigation whatsoever or software engineering. And so what we do, these silicon MOSFETs, they switch about 20 times faster than a traditional IGBT. So an IGBT will switch at around 8 kilohertz or less, and in that area, there are harmonics being introduced that you now have to mitigate with all these large reactors and harmonic filters and so on. But because we're going so high, we don't ever have to worry about those low-end harmonics. They don't exist for us anymore. We've pushed it all up into this higher frequency. And as a result, all of our filtering, our LC filters, our double-stage filters, output filters, they can now go on to the PCB. They're now at the solid state level. We don't have to worry about these large copper wound reactors and filters and so on. So that's a 200 time reduction in footprint of your filters. And so that's really the beauty of all of this as well. So part of our secret sauce is we have a double stage LC filter on the front end that is on the same board and is matched and in tandem with our EMI EMC filters. And then also on the back end, we're able to give this sine wave filter because we're using the same solid state filtration system as well. There's some additional things that we're doing. We're adding discrete filters that handle both sides. This is kind of what it looks like if you're to blow it up and take a closer look at the topology. We're also using multi-layers or multi-levels. And then we're using wave canceling algorithms. And these wave canceling algorithms constantly monitor and cancel out any stray emissions or leftover voltages and things like that. So again, just a quick review. The secret recipe is our patented algorithms. We have a multi-level architecture. All VFDs on the market are 2-level. We are 3-level, which is usually a medium voltage design because you can hide the cost of these things in the medium voltage, and you never used to be able to do that in low voltage. So we are a true 3-level VFD on both sides, the active front end side as well as the output side, which means we have much more steps, which contributes to a true sine wave. We're also using the silicon carbide semiconductors, and then the 200 times smaller filters that are now patented as well. And the result is we have a pure sine wave to the motor. The motor thinks it's on the grid. It is that clean. Now, as a result, I don't know if you remember at the very beginning of the presentation, I showed you a picture of our drives inside of a panel. And this is everything you need in the panel. There is no need for dynamic braking resistors, no need for sine wave filters, no need for active harmonic filters. It's all included in this little guy. It looks like a VFD, but it's truly a complete VFD filtered system. And so your footprint's now less, your costs go down for your packages, of course, transport, maintenance, and your energy consumption goes down. So now, with testing, we can show you that the motors run cooler. So here's an example of a motor on our drive and a motor on a competitor's drive. Somewhere in Northern Europe is where this one comes from. You'd all know the name. And at different loads and different speeds, you can see the delta differences in operating temperature. If you're running data centers, if you can get all those motors to run at 10% less, who wouldn't love that? That's a huge impact. Of course, extending the life of the motor as well. Here's a little video. Roger showed you the longer version of this video, but I'm going to play it here. And it's going to show you a sound difference. And this is a typical square wave from a competitor's drive running at about 82 dBA. And now here it is, the same motor on our drive getting a pure sine wave to it, and it's running about 10 dBA quieter. So that is a live recording. It's like we got a little, there we go. All right, so in summary, we've solved these VFD impacts right at the source by changing the VFD itself. So we no longer need these bulky filters. We've replaced that with an active front end with our special patents and designs and the switches. We don't need the sine wave filters on the load side or the DVD-TV filters or the reactors, and your motors end up running cooler. We don't need inverted duty motors or special VFD cables to take care of the spikes that pepper the insulation. Now you can use a standard motor. You don't need a NEMA MG1 part 31 anymore. Now you can go with a NEMA MG1 part 30. And you can use standard cable. You can still use shielded cable if you want, but you don't need that high-end insulation on your cables anymore. And then, of course, common mode voltage, which is a pain to most facilities because their motors break down so quickly from the bearing side of things. You don't need to add these chokes. You don't need to insulate your bearings, and you don't need the shaft grounding rings. By the way, if you've got hazardous location motors, let's say they're Division 2 atmosphere, you may have to insulate both bearings to avoid the shaft grounding because it may be considered a sparking device. You don't have to worry about that anymore. Our drives can sit as far away from the motor as you want, and they do not have to have insulated bearings or shaft grounds. And that's because we don't induce the voltage. You can use standard bearings. We do have white papers and case studies and so on that show our different applications. In this case, we're talking about long lead. This is just a quick blurb on that. The ability to eliminate all external filtering. If you have a harmonic issue, let's say at a hospital or airport control center, or other places that have very sensitive critical equipment, This solves the harmonic problem, and you no longer need to add these copper-laden filters. Again, whenever you need, we'll give you technical bulletins, white papers, case studies. And if you guys can come up with some case studies for us to add to that, that would be fantastic. Coming into the end of the presentation here, the drive itself, how it programs, a lot of people don't necessarily walk around with a laptop, so we've relied heavily on developing the mobile app. We still have a laptop connectivity that's coming, but the mobile app, you can fully control and program and configure your drive right from the app on your phone. And that's for Android and for Apple as well. You could do it over Wi-Fi, you could do it over Bluetooth. And here's what our HMI looks like. It is a full touchscreen HMI. And of course, there's a lot more you can set up here for scrolling and for displays and so on. We also have an IP66 version for this for any of the NEMA 3R or 4X paneling that you might want to do. For control, we've got what we've done is we've mimicked all the I/O that you normally get in some of the European brands out there, like a Schneider or a Vacon, things like that. So we've got the full 6 digital inputs. We've also got 2 STOs, 3 analog in, 2 analog out, and 3 relays for the 3 digital output as well, one of them being Form C.
Josh, quick question from the chat. Sure. Is the Wi-Fi or Bluetooth interface standard, or are they options?
They're included. They're native to the drive. Yeah, they're native. They're not an add-on. So that is included. Here is the range that we're doing. We have an S3 and S4 frame. Our S1 frame is almost released. It's pretty much there. And we go up to, presently, we go up to 75 kilowatt or 100 horsepower in 600 volt and 125 volt. That's our S4 frame. In 480 volt, we're at 75 to 100 horsepower. And then end of January, somewhere in February, we're going to have our 125 horse or 150 horse released. And that will cover pretty much everything you need for MCC range or panel range that you would normally do for wall mounts. And that's where we're going to hold it for now. We may develop larger horsepowers later, but right now we're just going to hold it there and continue to market that out and get that into the industry as needed. Here's a lot of our features. We broke up our Modbus TCP, BACnet IP, and Ethernet IP for our field bus protocols, because Ethernet IP is a beta version right now. So we're asking everyone to play with it, test it out. It's a working beta, and we're not just leaving it alone. We are supporting that right through to final release. So you can interface with any Rockwell PLC. We have the EDS files for it, and away we go. And those are native as well. So there's no add-ons for these. All 3 of these are included. It is a dual port Ethernet, and that's pretty much the future. We're keeping it as Ethernet. We don't have an RS-485 capability, only because we decided that this would be the future of where we're going with this. Where do we shine? We shine with places like data centers, hospitals, process automation like critical facilities, of course, buildings where interference from emissions has been a problem, and noise from motors has been a problem. Water, wastewater, again, harmonics are a huge thing in water, wastewater, and of course, oil and gas. But as you start to go down the categories of where else we can shine, we also have a less than 3% harmonic content down to about 50% speed. So, and partial loads as well. So there are some areas that require even more stringent harmonic mitigation than you would be asked for from this standard of IEEE 519. Retrofit's great for us because you can keep your old motors, you can keep your old cables. The example that Thierry was talking about just now, I believe. Was it them? I believe, yeah, they were. I think it was that the 14,000 foot cable length. Thierry, was that the?
Yeah, I mentioned it before the meeting started. Yeah, there's a 50 horsepower submersible pump
Oh, it's
1,400
just
feet away from the VFD, connected with an old underground cable.
nice. Yeah. So no need to upgrade your cable or your motor when you put our drive on there as a retrofit. That's a huge savings because your ROI is not impacted at all. You're still going to get that 7 to 11 month return on investment on your drive, typically. And then filterless applications where you want to save space in your facility and weight and so on. And then finally, regeneration. So we don't need a dynamic braking resistor because if there's any regeneration coming back, that gets put back onto the grid, and we do it better than anyone else because of our topology being a 3-level active front end. And that's
Josh,
pretty much it. Go ahead.
Emery had a quick question about how much less heat when compared to other VFDs. I answered that motor runs about 12% cooler. Is that correct?
Yeah, about 10%. It could be as much as 12%. Let's go back here. There was right here. Here's that slide. So we ran this specific experiment, our drive versus an ABB, and our motor was consistently about 10% less. It could be more, depending on what they're doing with the VFD.
And on that note, Kevin is asking, so the motor retains its service factor?
It can
believe that's
retain
a
its service
one-to-one.
factor. Yeah, you can retain as long as you got the FLA for it, we get to retain it. That's the one thing that NEMA MG1 Part 31 did. It took away the service factor if you put a VFD on it. But now you can keep your service factor, and it's not going to impact the over, because they did that in order to accommodate for the extra heat you get with a normal VFD. With ours, you don't get that extra heat, so you can keep your service factor now. Just look for the amps, and away you go.
And on that note, also asking, we use VFDs in refrigeration and HVAC compressors, which are cooled by the refrigerant, so the 10% less is not adding load to the refrigerant.
Okay, let me understand that. Here, sorry, can you repeat that question?
Emery, can you take the mic? Yeah.
Yeah, there's 10% less heat generated by the motor because most motors are, have encased in refrigerant when it's coming back from the evaporator. So that's not adding heat to the refrigerant.
Right.
So that was my point, was so if that's the case, because you're using data centers as one, and data centers are full of compressors with, I mean, we've seen ammonia compressors and all different ones. So I'm trying to figure out where's the optimal case, because we've been controlling compressors in a smart way. So we have a smart controller, and you're saying there's no RS-485, no Modbus or anything like that?
Correct. It is straight Ethernet. So is it a situation where you need the RS-485?
Well, the controller that we use communicates with the drive via RS-485, and it's basically saying, hey, what's your torque, what's your kW, so that it gets feedback to know, hey, the torque just increased, which means there's a bigger load, I got to speed up or something.
Right.
I don't have the exact code of why, but logically that makes sense to me.
Right. We can get a converter that will give you so that Ethernet will go into the converter, and then it'll be RS-485 to where you need it on the mod. And it's because we have Modbus TCP as well.
Yep.
So I'm sure you've seen those converters, and so we're able to do that
You
as
have
an
Ethernet capability, Ethernet cable?
Yeah, Ethernet cable, absolutely.
Okay.
Yeah, dual port.
We
So
have yeah, go ahead.
I was going to say native to the drive. I don't know if you heard that part. Is Modbus TCP, BACnet IP, and Ethernet IP. So those are native to the drive. And those Ethernet ports, if you can see right there down here, these two are for extended. One's reserved for future. One's for extending the remote mounting the keypad. But the dual Ethernet ports are for field bus.
So does that mean you could have one controller controlling multiple drives if they synchronize?
You can, and of course, we've got a full software team right in Montreal. So if there's anything oddball you want to do with that, depending on how you want to cascade or master slave, etc., daisy chain, we can tweak the software for you as well.
Okay, very interesting.
It's kind of nice to have a manufacturer in your backyard on this side of the border. Right. So being a North American provider, right? So it's in a North American time zone, Eastern time zone, and of course everyone is happy to be part of the 51st state. So we're all good. That was a joke. Yeah.
No, we're supposed to make politics out of this, guys. I'm just teasing.
Sorry, did someone was gonna had another question? I cut them off. I apologize.
Sorry about that. Yeah, there was. We have 3 more questions. One was, what about higher frequency harmonics, as it is one of the disadvantage of active front end?
Right, traditional active front end that has been around for a bit now. They let me just get back to where are we here? Right here. Yeah, so the traditional active front end, they're using IGBTs. So they're going to be switching down in that 8 to 5 kilohertz down in there, 2.5 kilohertz. We're way up at 105 to 210 kilohertz. So we're not producing any of the harmonics down at that lower end. We've pushed it all up into this higher end. And that's where we focused all of our double stage LC filters. So there's no more interharmonic problems. There's no high order frequency problems at all. So that's our claim to fame, is that we've taken care of all harmonic issues right up to the 210 kilohertz and beyond. So there are no higher level frequency issues with us because of the design.
All right. Thank you, Josh. A couple more. Let's try to accelerate to make sure everyone has at least the first answer, and then we can follow up by email with everyone. Kevin here had another question. There are Ethernet serial converters available. Oh, that was as an answer.
Nice.
Quick question about, pricing. I know you had another sheet to do a price comparison. If you want to pull that up, I'll take that moment to answer another user saying max available VFD power. By the end of Q1, it's 125 horsepower. Right now, our range goes up to 75. So that's the current one. And once you're done with the pricing, we'll pass the mic to Chris here, who says he has questions too. So just address the question, then pass the mic to Chris, please.
Great, not a problem. We got a little chart here that shows a typical cost. Let me pull this down. And I've got some other comparison sheets as well for panel packaging and whatnot, where we really shine. If you're just up against a standard 6-pulse drive that's naked, it's got no filtration on it whatsoever, we're going to be about double the cost of that, because we're including line and load filtering at a high level. But the moment you start adding to it, the moment you start adding any kind of reactor, or the costs for special cabling, the costs for different installations and things like that, then we start to become on par. We start to bring that cost even. And then, of course, as you add more and more filtering, we're now the cheaper option, and so on and so forth. what I like to say, rule of thumb, is if you just got one reactor, we're going to be probably about 20% more because you have to package all of that. But the moment you go double reactors and beyond, we are the better solution, not just from a cost perspective, but from a size of panel perspective. If I want to go back to, let's take it back up here. This guy here, right? So we no longer need to do any of these packages in our panels. So that brings everything down. I recently did a quote for a customer that had 11 drives in an MCC. Each drive had to have a load reactor, and then they had one huge Mirrors filter as a harmonic passive filter on the front end. It's for a lab. And we instead gave them the option to go with the SmartD. They were able to reduce that MCC by 12 feet. And that drastically reduced the MCC price. So now we're just waiting to hear back on how that bid comes along. They're concerned because they've got a Rockwell PLC, and Rockwell is saying they may need to put in a Rockwell VFD and so on to keep their service guy happy. So he's still making some money on the things he's supplying, all the filtering and stuff like that. So there's a little political game going on, but regardless, this shrinks everything down, keeps your costs down. So I'll send you if you guys are cool with it, I'll send you a little comparison that's similar to this. It's just a little bit more easy to digest, and I'll send you this page as well.
Sounds good. Thank you, Josh. Chris, are you in a position to take the mic?
Yeah, sure. Can you hear me?
We hear you fine.
Great. Yeah, I was just the bit that I kind of struggled with a bit is the physics. I just the higher switching frequency. I'm just not sure how that solves the issues with bearing damage and so on that we've kind of seen in our industry.
Right. So coming back to the way that we're putting it all together, because it's not just taking care of higher switching faster. It's also filtering it with our patented filters. So those filters coming down on the PCB level. So our output sine wave filter and double stage LC filters and common mode filters are all at the PCB level as well. So that's why we have a pure sine wave going out to the motor. The motor has absolutely no bearing discharges at all. There's no shaft currents at all because it is a pure sine wave. There's no longer a square wave coming out of that. And so so there's no high frequency harmonics happening on the load side either. I don't know if that makes sense, but it is that combination of the silicon carbide MOSFETs plus the wave canceling algorithms plus the solid state filtration.
Yeah, it kind of makes sense in that the kind of a low pass filter gets smaller when you're trying to cut off the higher frequencies. So I kind of get that part of it. It's just the magic bullet part where the filter is smaller. I understand that, but why are these problems vanished when we have the faster switching frequency?
You don't have
sorry. Well, because we're no longer switching at the old 40-year-old IGBTs, right? Which is an 8 kilohertz or 5 kilohertz and so on, right? Maybe I'm not explaining it as well.
Plus the one, I'm going to jump in a second. Plus
Sure.
The differential is when you are producing a pure sine wave output, you don't have all that extra part of the sine wave, that square, that basically has to go somewheres in the circuit. So if it isn't there, it can't radiate into the motor. And that's where I think a lot of it goes away. I was quite astonished when I first saw the output waveforms of these drives. And me being in the motor industry for, my entire life, and then I've ran into a lot of these issues also about bearing failures, long lead issues. Even the grounding rings have some issues, is that if you read the fine print, they say, well, you got to check those grounding rings to make sure that they're not, getting like a film in between them. So you're supposed to clean the grounding rings. Well, guys just don't do that stuff. They need to have the old motors that they've had in there, like that my father would have put back in, back in the 60s and 70s, where there were no VFDs. They did it all mechanically on the speed control. So.
And one last thing, Chris, is because it's a true sine wave, it's like it's on the grid on utility. So when a motor's on the grid, there is no discharge happening on the bearing, and that's what's happening here. There's nothing to discharge. We have no DVDT issues or reflective wave issues, and common mode is not an issue at all. So when we turn the mic over to Chris Richards, we turn the mic over to Chris Richards?
No, it was Chris.
It was another Chris. Okay, I was going to say maybe Chris. Chris, I don't know if you'd like to weigh in on that. I don't know if you're still with us.
Oh, I am, but you're good.
There you go. Yeah, you're good.
He says you're good. We'll send you a case study also about Energy here who had to change the drive due to bearing issues. Might give you more information in there. We've got Kevin Baker here saying, I'm starting to see more specifications calling for active front-end drives, particularly in water, wastewater applications. That is correct. We're seeing a lot of growth in the water, wastewater application, and a lot with submersible pumps as well. I guess that's due to the size of the machine. Hard to extract, so if you want to control it, you're going to need a VFD that can not destroy that motor. User, I don't have your name, but ask for the power range, and then we can move to Emery's voltage and sizing question. Maybe you can take the mic after that, Emery, but for now, can you give the power range again?
Yeah, so we're looking at basically 15 horsepower through 125 horsepower in 480 volt. That 15 horsepower, right now we're running smaller horsepowers with it, but our S1 frame is coming, so we'll get down to 5 horsepower, and that will be taking care of anything below 5 in fractional. But again, because it's an integrated system with full filtration, not a lot of people need 519 levels of filtration at that low horsepower, but it's there. Where a lot of people are going to really enjoy the benefits is on the back end, and for where you're putting multiple motors on a VFD, like in a data center, etc. So that is coming, and hopefully that actually reaches about 80 to 90% of the low voltage drive need out there.
Thank you,
Hope
Josh.
that helps.
Emery, do you want to take over the mic?
Yeah, I guess basically the question is it 208 volt to 460 volt? Both?
Right now it's 480 and 600 volt.
Okay, so
we don't have the 200 through 240 volt yet. Again, that's part of our S1 development.
Yeah.
So that's coming.
No, we do both, but I'm just curious. Sure. A lot of the small compressors that would be in, let's say, even data centers, they're, typically 208 volt scroll compressors.
Sure.
And, so some of those are, we have customers that are, let's say, convenience stores or restaurants, and they have a lot of stuff. And what we've been doing in the past is we look at, okay, if we put together a 10 horsepower panel or whatever, it'll take care of anything underneath that, because otherwise you'd have to stock too many sizes,
too many permutations. That makes sense.
And then the other thing is the compressors in refrigeration, when they start up, they're starting under load.
Okay.
So I don't know if that's an issue for you. And then in terms of sizing the compressor, the drive, so do you make it 10-20% bigger? Because I think that's what they're doing now, is they're making it almost 20 or 30% bigger drive than they need just to be on the safe side.
in order to handle the loaded start.
Yeah, I don't know why. They just do it. It's like free insurance.
Well, one of the things that we've done is our drives are rated at 50-degree ambient max, and we've designed around that. So we may not necessarily need to oversize anything because once we go to a 40-degree ambient max, our current ability goes up. So there is a good chance, 99% chance that you wouldn't need to upsize this drive for that situation for a loaded start. But yeah, it does happen. One of the things you might be interested in too, Emery, is we have a 480 volt single phase development on right now, where we're still going to have that active front end with the single phase. In other words, you're going to get a single phase input drive that has no harmonic content, so, or the 519 harmonic content equivalent. So that's another item that's coming that may be of interest for some of your customers too.
All right, thank you.
Yes, sir.
Another maybe take, if you have a final question, guys, put it in the chat. We're running towards the end here. Kevin Baker is asking, can you expand on a 3-level architecture?
Sure. So 2-level architecture. Let me see if I can go back to sharing this screen here. 2-level architecture is what all low voltage drives have traditionally been. And I'm just going to go back to, give me a second here. It has to do with layering of your devices. Where did you go? It was just here. We just showed it. Well, let's go with this one. Okay, so this is a 2-level drive, right? So 2-level drive, you got tandems going on here of your IGBTs. What they've done is they've used something called cascading H bridges or other types of topologies to feather in more pairs or more units of IGBTs in order to break down the number of steps that you have between your sine wave steps, I guess, how you create your sine wave. So this one here, it's pretty raw. It's showing, if you will, it's like a 6 pulse, but on the back end, right? But these 2 levels, that's what's on every drive that's out there on the market. We're the first ones to really, maybe not the first ones, but the first ones to mass produce, because I'm sure there's some custom made product out there by somebody that has brought in this multiple layers or multiple levels of switch tandems, right? So by doing that, you're able to now contribute to a much better sine wave. I don't know if that makes sense. Was I able to explain that to you a little bit? If you know medium voltage drives, I wish I had my medium voltage drive slides. I could show it to you. It's a little more clear. I don't think we have as clear a showing on what the 2-level and 3-level is, but we are trying to show that here in what we do. So it's layered. Cartridges, if you will, of or packages of switches going into the output to create an even smoother sine wave. So that's one of the contributing factors. It's part of our secret sauce. So when we're talking about our secret recipe, if you will, we've got these algorithms for switching, but we've also got this multi-level architecture. And that's what we're referring to. There's no one else out there that has a 3-layer active front end or a 3-layer output. And no one else is using the silicon carbide semiconductors as well. So it's a combination of things that's bringing us the sine wave, and that's what the multi-level or multi-layer architecture, people call it a topology. That's where that comes in. Again, you'd see it a lot in medium voltage. It's really the first time it's being mass produced on low voltage.
Let's take a last one and then pass the mic to Roger for closing. What is the impact of high switching frequency on switching losses and efficiency?
Sorry, repeat that again.
What is the impact of high switching frequency on switching losses and efficiency?
Okay, so yeah, because you can't get something for nothing. So you are getting higher heat, and you're getting higher EMI, and you're getting higher DVDT. But because of these silicon carbide MOSFETs, they can handle the heat. They do not break down. Whereas an IGBT, over time, they've had to make them silicon carbide IGBTs, but it's still that slow switching. But they had to handle that heat with the silicon carbide. So silicon carbide has been a game changer in the ability to handle heat. So not a problem there. When it comes to higher EMI, because we're now pushed up into the higher switching, we can now put EMI filtration right alongside of our LCL filters and so on, right? So that's all together on the board. So we have EMI filtering that's patented, that's just for us to handle the higher DVDT. So Danfoss, for example, bought a company called Semicron, who makes silicon carbide IGBTs and MOSFETs and so on, but they can't switch at our same speed because not only the patents, they just never got to that design. So even if they wanted to, they can't do it. So yeah, so there's a patent on how we do our filtration on those higher spikes on the DVDT and the higher EMI and so on. So like I said, we can't get something for nothing, but then we've taken the next step and brought all that filtration in to handle all that.
Thank you, Josh. Thank you, everyone, for being here. Roger, do you want to have a final word here?
Yeah, I just want to thank everyone for joining us today. If you do have other questions or things like that, I'm going to put my email down here and I'll pass it along to them. Also, I do run classes on multiple things, including I work with a company that actually builds submersible pumps, and they have to even build a special motor just to handle the spiking power from VFDs. If you're going to put their pump on VFDs, you got to use their special motor plus a long lead filter. So you got to remember that when you can buy a standard motor, standard, THHN wire is fine in the building. You don't have the noise. I think it's really what Tesla originally had in mind is, clean waves, noise radiated, not only in this industry, but other industries that are out there. I see, a lot like out here in the agriculture industry, we run into the power from all of the solar that's been put in is giving crazy voltage imbalances and spikes. But I found this to be a very clean drive, and that's why I wanted to recommend it. So I thank you for your time. And like I said, I'll put my email down at the bottom and you can copy it or you want. I think I've probably connected to most of you anyway. And I'll continue to as updates come about, I'll be posting it on my LinkedIn. So
Thank you, everyone.
thanks everyone.
Have a good day.